In this video, we're going to do an intro to linear combinations. Let's take a look at an example. The problem is to write the vector w, 1, 5, as a linear combination of vectors u and v by graphing. Let's make a sketch of u, v, and w. Here's our sketch of u, v, and w. Now let's recall what exactly a linear combination represents. So when we say linear combination of u and v, algebraically what that represents is taking some constant c1 times u and adding it to the vector c2 times v, where again c2 is some constant. So constant times u plus a constant times v. Now, what c1u represents geometrically is traveling parallel to the vector u, possibly in the backwards direction. So what I'm going to do is just add this dotted line here to our sketch, representing these different possible multiples of u that we could be taking. So effectively, we've just drawn in a u-axis here. Similarly, this vector c2v here represents traveling in the v direction, possibly backwards along v. So I'm going to just draw in another dotted line here representing this v-axis. Okay, so there we go. There's our v-axis. Now our goal is to find two vectors, one parallel to u, the other one parallel to v, which add up to the vector w. So let's take a look at our sketch. If we were to travel this distance along u, just to about here, we would now be in a position where we could travel over in this direction, which is parallel to v, to create two vectors that sum to w. So if I draw this one in here, here we go. We've got a multiple of u plus a multiple of v, which equals w. Now taking a look at this vector here might be a little bit easier to visualize this by actually drawing this vector down here. So we're just going to draw a shifted version of that vector starting at the origin. So this vector that we've just drawn is in standard position. This is the same vector here in a different position. So taking a careful look now at our sketch, this vector here is exactly 2 times the vector u. That is because it has components 4, 4, so it's exactly 2 times the vector 2, 2. This vector, which we've then drawn in at the top of the sketch here, it travels 3 units to the left, 1 unit up. That makes it exactly negative v, so we can label that on our sketch. Similarly, we could label this vector here negative v if we wanted. What we've now found is that 2 times u plus the vector negative v, so in other words 2u minus v, is equal to w. So we have solved the problem by graphing, or we solved it geometrically if you want to say it that way. If you want to check your answer algebraically, you could write 2 times the vector 2, 2 minus the vector 3, negative 1, and just check that that does equal the vector w, which is supposed to be 1, 5. And yes, indeed, that does work. Later on, we'll see how to solve this problem algebraically, meaning without drawing the sketch.